purpose of this lab is to observe the motion of a mass swinging in an arc while oscillating on a spring. In our example, our spring primarily oscillates from left to right with some movements in the up and down directions, unlike in the demo where the spring solely travels up and down. As the mass oscillates, not only are we tracking its motion, but we are tracking the change in energy as well. In order to accomplish these goals, I will be incorporating Newton's second law of motion as well as the energy principle. Newton's second law suggests that when an object is acted upon by a force, its velocity will change. For this lab, we are going to focus on the external forces of spring and gravity. The energy principle states that the change in total energy is equal to the sum of all changes of energies. For this lab, we are focusing on the kinetic, gravitational potential, spring potential energies. In the end, the change in total energy should be equal to zero according to the energy principle. For this lab, I observed the motion of a given object as it swung in an arcing motion and oscillated on the spring. I was able to track the object's motion and collect data through the program tracker. From rest, I took the length of the center of the object to the fixed attached point, which was 0.7 meters, in order for the program to calibrate the measurements. To gather the best data, I started tracking the object at frame 6, which is the last frame right before the object starts its arcing pattern, and stopped tracking at frame 103, which is the last frame. I let the video play until the end so I could have as many oscillations as possible to gather the best data. The mass is at rest, it has no initial velocity, but its initial position is negative 0.004 in the x direction, negative 0.167 in the y direction, and 0 in the z direction. For each following frame, the object's position and time was recorded by using the point mass tool. Next, we need to find the spring constant in L naught. To find the spring constant, we need to know the period of oscillation, which is found by taking the time at the third trough and dividing it by 3. Once the period was found, we plugged that value into the respective equation and found the spring constant. After finding the spring constant, we were able to take that value and plug it into its respective equation as well. Since the mass was given and we found the initial position, L naught, and the spring constant, we were able to transfer that data to our code in VPython. In VPython, we are going to use the values collected from tracker to create a predicted model of the object oscillating. First off, we're going to plug in the values of mass, L naught, spring constant, initial position, initial velocity into the code. Next, we specify L, L hat, and S in order to calculate the spring force and spring potential energy. After defining the variables needed for the spring, we are able to rewrite the equation that will define our energies in the system. After defining our energies, we are to define our net force, which would be comprised of the spring force and gravitational force acting on the object. With the net force found, we can use Newton's second law to update the velocity and the position. With the updated position, we can find the updated length and direction of the spring. After completing the computational model, the program produced a graph with multiple lines representing different energies. Green is the change in spring potential energy, red is the change in gravitational potential energy, blue is the change in kinetic energy, and the orange line is the change in total energy. The change in total energy supports the energy principle because it stays around zero, but where the issue comes in is with the spring potential energy. As the spring energy comes up, it tends to level out at around zero, then continues with its path upward. I believe this is an issue I created when using the point mass tool to track the object, but other than that, the kinetic energy and gravitational potential energy looks accurate. Other than the spring potential energy, the observational data was relatively accurate to the computational model's data.
Part 1. Yes, the energy principle is satisfied. By looking at the graph, the change in total energy stayed around zero, which supports the definition of the energy principle, which was stated earlier in the video. Part 2. After finding the period of oscillation for the x and y components, the values came back pretty similar. For the x component, I got the period of oscillation to be 1.583 seconds and the y component to be 1.456 seconds. The periods are off by a little more than a tenth of a second. I feel the oscillation for the y is quicker because the focus of the oscillation is more east to west in the video rather than north to south, so it creates quicker periods of oscillation in the y component.